All right, so let's start the classwork problem for chapter number 20. Okay. All right, so let's start with question number 1. So what we are given here. So we are given a current carrying wire that carries a current this, and the length of this wire that is inside the magnetic field is 12 centimeter. And the direction and the magnitude of the magnetic field is 0.90 Tesla. The angle the wire makes with the magnetic field is 60 degree. Okay, and we have to determine the magnitude and direction of the force on the wire. Okay, all right, so let's see how to solve this. Okay, so in theory lecture we learned that the magnetic force on a current carrying wire that is in a magnetic field is equal to this. Okay, so we are given actually everything: 30 amp, 12 centimeter, 90 Tesla, sine 60 degree. So if you plug all these values in your calculator, you should get this value. And second right hand rule tells us the direction is into the page. Okay, so here I mean you can see also this. So try your right hand rule and see that whether you get the direction that is into the page. Okay, all right, the next one. So next one says that we have a magnetic field, and that magnetic field, I mean in that magnetic field we have a loop. Okay, when the magnetic field is 0, okay, so this loop is basically hanging from a balance. When the magnetic field is 0, the balance shows that the force is 0. Okay, the force is 0. Okay, so the force is 0 on the balance when magnetic field is equal to 0. When there is a magnetic field, it shows the force is equal to this. Okay, and when the current in the loop is this. Okay, and we have to calculate the magnetic field, and okay, so basically the magnitude of the magnetic field B. Okay, and one more thing is given here, that is uh, this length. Okay, 10 centimeter. All right, so let's try. All right, so here you see that this part is out of the magnetic field. Okay, so this part is out of the magnetic field, so there will be no force here. Okay, so I mean there will be no magnetic force here basically, and then there will be magnetic force here and here. Okay, now you see that the magnitude of the magnetic field is uniform here. Okay, everywhere in this problem. Okay, now the same current is flowing here and here. The length is same, but the current directions are opposite. So what we get, the force here is in this direction, and the force here we will get in this direction. But the magnitude of the force here and the magnitude of the force here will be the same. So that means they cancel each other. Okay, so we'll have force there, but two forces cancel each other. Okay, so this force cancel with this one. Okay, so we have only force due to this part. Okay, now let's try to calculate what is this force. This force will be I L B sine theta. Sine theta here will be sine 90 degree because the current is going in this direction and the magnetic field is out of the page. So you see that they are exactly sine 90 degree, 90 degree. So it will be 1. So B, the magnetic field, the magnitude of the magnetic field can be determined by by solving this equation, and that is equal to this. And here F is 3.48 times 10 to the power minus 2 Newton. Okay, I is 0.245 amp, and L is 10 centimeter. Okay, and this tells us that magnetic field will be 1.42 Tesla. Okay, all right. All right. Number 3. Okay. All right. So we have two pictures given. Okay. It says that when the proton, so proton, you remember the proton is a positively charged particle. Okay, is moving vertically upward. The force is this. Okay, force is this, and the direction of the force is towards west. Okay, and the speed is also given in this case. Okay, so the magnitude of the speed is this one. Okay, and it also said that when the moving horizontally in a northerly direction, that means figure B, the force on the proton is 0. Okay, so when the force is 0, so the force is 0 when when okay, so force is 0 when sine theta is equal to 0, right? The minimum force what we get is 0. So when sine theta equal to 0, sine theta equal to 0 when theta equal to either 0 degree or 180 degree. Okay, so that means when V and B are either parallel or anti-parallel. Okay, so for simplicity, just think that when they are parallel, when theta equal to 0 degree, right? So this information can tells you about the direction of the magnetic field, okay, which we are basically asked to calculate. Okay, so here you see the determine the magnitude and direction of the magnetic field. But this information, okay, by using the information, this information, we can tell that the direction of magnetic field and direction of the force, direction of the velocity in this case are the same. Okay, so here it says that moving into the page north. Okay, so that means the magnetic field's direction is into the page. Into the page means, okay, so sorry, into the page means cross. Okay, so we already determined the direction of the magnetic field that should be into the page. Okay, so that is the direction of the magnetic field. Okay, now let's try to calculate the magnitude of the magnetic field from this part. Okay, so F equal to I, not I, so this is Q V B, and if it is into the page, then the direction of V and B will be sine 90 degree. Okay, so that is equal to 1. So QVB. So then we can determine the magnetic field by solving this equation. Okay, so here F is given 8 times 10 to the power minus 14 Newton. Proton's charge is 1.60 times 10 to the power minus 19 Coulomb. Okay, and velocity is here 5 times 10 to the power 6 meter per second. And if you plug these values in your calculator, you should get the magnetic field that is equal to 0.10 Tesla. All right. All right, so here it says that an electron is traveling at this. So this is the speed, right? So speed is given, magnetic field is also given, and it says that perpendicular, the direction is also given, and then we have to calculate the radius of the electron's path. Okay, radius of the electron's path. So we already calculated, I mean, we already derived this equation, right? R equal to mv qb. Okay, so if you forget, please review it. Okay, so by using the magnetic force and the centripetal force, we derive the radius of the curvature, the expression for the radius of curvature, right? Okay, so then use this equation and then determine what is the radius of curvature or radius of the electron path in this case, for example. Okay, so the mass of an electron is this, very small, 9.11 times 10 to the power minus 31 kilogram. Speed is given 1.5 times 10 to the power 7 meter per second. Charge is 1.60 times 10 to the power minus 19 coulomb, and the magnetic field is 0.010 Tesla. So this is basically equal to 0.0085 meter. Okay, all right. So it says the next one says that an electric wire in the wall of a building carries a current that is equal to this, vertically upward. Okay, what is the magnetic field due to this current at a point P 10 centimeter due to north of the wire? Okay, so here basically we want to know what is the magnetic field, right, at a distance 10 centimeter from the wire. Okay, so this can be determined by using this equation, mu 0 over 2 pi I over R. Okay, so what is mu 0? Mu 0 is 4 pi times 10 to the power minus 7 Tesla meter per amp, and then 2 pi, and I is 25 amp, and P is 10 centimeter. 10 centimeter means 10 to the power minus 2 meter. Okay, so that means this is equal to 0.0005 Tesla. Okay, and then again, using the first right hand rule, you can determine what is the direction of the magnetic field. Okay, a very similar question here, but here we have two wires. So here you see that one wire, another wire. So the current in one wire is out of the page and one is into the page. Okay, so it tells us to find the total magnetic field at this point. Okay, all right, so let's first calculate B1, mu 0 2 pi, and that should be for I1 and R1. Okay, so mu 0 is 4 pi times 10 to the power minus 7 Tesla meter per ampere. Okay, 2 pi, and then I1 is 5 amp, and R1 is just this 5 centimeters, so 5 times 10 to the power minus 2 meter. So what we get is 0.00002 Tesla. Similarly, you can determine what is B2. This is 7 amp, and again the distance is 5 centimeters, so 5 times 10 to the power minus 2 meter. So plugging all these values in your calculator give you this Tesla. Okay, now we have to calculate the net magnetic field and direction. Okay, so we have to understand the direction for each magnetic field to determine the net magnetic field. Okay, so first let's try for B1. Okay, so the use the first right hand rule, and now here this I1 is out of the page. So if it is out of the page, you can see that the direction of B1 at this point is this. Okay, so it is upward. Okay, and the same thing by using the right hand rule, first right hand rule, you can show that the direction of B2 at this point is again upward. Okay, so the direction, both directions are the same, that means upward. So the net field will be just sum of these two. Okay, so it would be 0.00002 Tesla plus 0.0000028 Tesla. So it is 0.000048 Tesla, and the direction is upward. Okay, all right. All right, so we have two wires, 2 meter long. Okay, so two wires, 2 meters long, 2 meter longs, and 3 millimeter separation between these two wires. Each carries current 8 amp. Okay, calculate the force on wire exert on each other. So we have to calculate the force. Okay, now here it asks us to calculate only the magnitude. Okay, but now you know that if they are parallel, then they attract each other. If they anti-parallel, then they repel each other. So you already know that, right? So here, fortunately, you don't need to do that. You just need to calculate the force. And the force is this mu0 2 pi I1 I2 d times L. Okay, so you know everything here. This is 4 pi times 10 to the power minus 7 Tesla meter per amp. 2 pi, and I1 and I2 are both same, so this d is 3 millimeter. 3 millimeter means 10 to the power minus 3, and L is 2 meter. Okay, so if you plug all these values in your calculator, you should get something like this. So the force is this. All right, so the last one. Okay, so the last one tells us that we have a circular loop of wires has a diameter. So we are given the circular loop of a diameter that is 20 centimeter. The number of loop is 10, and the current in the loop is 3 amp. Okay, and the coil is placed in 2 Tesla external magnetic field. Okay, so we have to calculate the torque. Okay, maximum and minimum torque. Okay. So because sine theta is equal to 1 when theta equal to 90 degree, so the maximum torque we will get when theta equal to 90 degree, and minimum torque we will get when theta equal to sine theta equal to 0. That means when theta equal to 0 degree. Okay. So okay. So torque, if you remember, the equation we derived was something like this: N I, so N is the number of loop, I is the current, A is the area, B is the magnetic field. Okay, sine theta. Okay, so um, actually the last equation we derived was something like this: MB, right? MB sine theta. So it's basically the same thing. M is the magnetic dipole moment, which is equal to NIA, and then B, and then sine theta. Okay, so tau max is this NIA B when sine theta equal to 1. Okay, and tau mean will be when sine theta equal to 0. So when sine theta equal to 0, tau mean will be just 0. Okay, so tau mean is equal to 0, tau max is equal to this. Okay, now N is equal to 10 loops. Okay, I is 3 amp. Okay, area is pi diameter square over 4, right? So area is equal to pi r square. So r means d over 2. So the radius is half of the diameter, right? So d over 2 square. So it is pi d square by 4. Okay, and b is what? B is 2 Tesla. Okay, so 10 3 amp pi 4, this is 20 centimeters, so 20 times 10 to the power minus 2, and again square. Okay, so make sure you do all these steps. Okay, and then plug all these values in your calculator. So if you plug this values in your calculator correctly, you should get the maximum torque is equal to 1.884 Newton meter. Okay, all right, it looks like that's the last one. So that's it. In the next class, I am going to start chapter 21.